Hello everyone, my name is SR Shahjan. I'm from ECB section. My roll number is 23401A0483. I'm giving a PPT presentation in EMTL, the topic called Effective Effect of Frequency and Transmission Line Characteristics. So let's get in. Effective of frequency on transmission line characteristics. This presentation explores the impact of frequency of transmission line characteristics circular for understanding signal behavior in high-speed circuits. Well, we'll cover fundamental concepts, dependent parameters, signal uh, destruction, impedance matching, and uh, mit- mitigation techniques. The insights provides are essential for engineers designs modern communication systems. Transmission lines basics definition. A transmission line is a guide medium designed to transmit electric energy effectively from one point to another point. It's a fundamental concept in various communications and electronic systems. Key parameters, characteristics impedance, that is the dot, progression constant, that is y, uh, constant is alpha, phase constant is beta. Types of transmissions line, coaxial cubes, micro stripe, straight strip line, and twisted pair. Examples, RG85 coaxial cable has a Z0 of 50 ohms, ideal for radio frequency applications due to its consistent impedance and shielding um, properties. Characteristics impedance Z0 versus frequency. Phase properties. Z0 is determined by the physical demonstration and dielectric properties of the transmission line, which are designed to maintain a consistent signal path. Formula calculated as Z0 equals to root of L by C, where L is in indicated per indicatance per unit length, and C is capacitance capacitance per unit length, highlighting the balance between these parameters. Skin effect. A higher frequency current flows permanently on the surface, alternating indicates, and to the lesser extent affecting Z0. For example, a microstrip line can maintain a Z0 variance of less than 5% up to 50 Hz if carefully designed, showing the stability achieved by properties design. Frequency dependent losses. Conductor losses results from the skin effect where resistance increases with the square root of frequency, that is, or parallel to root of pi f mu sigma, that is illustrating the direct relationship with frequency. Dielectric losses energy display disappeared in the dielectric material due to the uh, polarization. The losses tangent, that is tan gamma, increases with frequency, uh, exacerbating signal loss. Radiation losses become significant at higher frequencies with the transmission lines is not perfectly shielded, causing energy to the radiated away from the line. FR4 dielectric material commonly used in PCBs exhibits an increasing losses targets above 1 GHz, significantly inflecting signals, alternating and performance. Attenuation constant alpha. Quantification: Alpha quantifies the signal loss per unit length, indicating how much the signal degrades as it travels along the transmission line. Formula: defined as alpha equals to R by 2 Z naught plus G Z naught by 2, where R is resistance and G is conductance per unit length, showing the factor contributing to alternating alternation. Impact: Im, im, impacted by skin effect and dielectric losses with higher frequency leading to gather attraction attenuation due to increased losses measured in per meter np by m or describes per meter per instance. A cable with alpha equals to 0.1 dB by m at 1 GHz will have a signal uh, reduced by 10% after traveling 1 meter. Phase constant beta. A velocity of propagation Vp, which is phase shift. Beta represents the phase shift per unit length. Formula, that is B equals to omega root of LC, L into C, where omega is the angular frequency demodulating the relationship with frequency and line parameters. Signal speeds. Vp is the speed at which the signal propagates. Formula Vp, that is omega by beta, that is 1 by root LC. Dielectric impact. Di- Dielectric constant E of R affects Vp higher results in lower Vp because the signal propagates slower in different dielectric mediums. Signals travels to the transmission line where will have Vp, that is equals to C by 2, where C is the speed of light, which shows how dielectric properties affect signal speeds. Signal dispersion, um, different differentiating frequency components of a signal travel at different uh, spreads, causing pulse spreading and signal degradation. Atten al- alternation. Frequency depending alternation alters the signal frequency spectrums, changes the shape and characteristics. Group delay. No constant group delay causes difference between frequency to arrive at different times, further distortion the signal. A square wave signal transmitted over a long transmission line will appear rounded due to dispersion and alternation affecting data integrity. Impedance matching and reflections. Reflections occurs when the impedance of the transmission lines does not matches the load impedance, leading to signal de- degradation. degradation. Mismatches. Voltage standing wave radios VSMWR uh, quantifies the impedance. Mismatches indicates the severity of reflections. Effectives. Signal losses, disruptions, and protolation damages to the source and effective of reflections, emphasizing the importance of matchings. Networks. Impedance matching networks must be designed for the operating frequency range, showing frequency specific designs and improvity treatment treatment. 75 ohms cable connecting to a 50 ohm source will result in reflection. demonstrating the impact of mismatched impedances. Techniques to migrate frequency effect. Material sections choosing low loss dielectrics like PTFE or ROX materials to minimize dielectric losses. Control. Uh, Prices controls of transmission line demonstration during manufacturing to maintain consistent impedance matching using lumped or elements to match impedance, reducing reflections and signal losses. Using a serial capacitor at the transmission to pre-empathizing high frequency components can comprehensions for frequency demodulations. Conclusion. Impact. Frequency significantly impacts transmission lines characteristics, affecting signal integrity and overall system performance. Importance. Understanding these effects is crucial for high-speed digital and RF circuits designs, ensuring reliable communication systems design. Proper design techniques and material selections are necessary to minimize signal distortion and losses, optimizing system performance. Continue research into low loss materials and advanced equation techniques are further trends showing the ongoing effect to improve transmission line performance. So that's it. Thank you.